Hey, it's Mr. Lum, and we're going to be doing some KEQ calculations. So KEQ is just a ratio of the products to reactants. And in the last lesson, we looked at how to make a KEQ expression or like a KEQ equation. So a few things about the KEQ expression is that since it is just a ratio of products over reactants, so what is the meaning of the KEQ? So a large KEQ means that there's lots of products. So since it's reactants turn into products, if there are a lot of products, like say if this is like 10 at equilibrium, and this is say 2 at equilibrium, then what we would do is our KEQ expression would be KEQ equals 10 over 2, or in other words, KEQ would be 5. So what we would say is that that would be considered a large KEQ value. And that means that there are a lot of products at equilibrium, right? There's like a 10 to 2. So a large KEQ value just means greater than 1. Greater than 1. Okay? That's what a large KEQ value means. Now, if we had something different, like say if we had these things kind of reversed right here, and the reactants hypothetically were 10 and the products were 2, and so they'd be products over reactants, 2 over 10, okay? Or in other words, KEQ would equal 0.2. So a small KEQ, this is considered a small number. A small KEQ means that there's lots and lots of reactants. So a small KEQ means a lot of reactants at equilibrium. And the value of small is less than 1. Okay, KEQ cannot be 0 since you cannot have negative concentrations of anything. So KEQ will always be a positive number. Now, a few things to remember. Temperature is the only thing that can affect and change the KEQ value. Concentration changes, pressure changes, catalyst, decrease in volume, increase in volume, all of that kind of stuff will not change the value of KEQ. The only thing that'll change the value of KEQ is temperature. Okay, so now that we have that, let's get into some calculations. So I have our first one right here. I have a little kind of like a step-by-step of what we should be doing first. And so the question says, 1 liter reaction vessel contains 0.75 moles of carbon monoxide and 0.275 moles of water. After an hour, an equilibrium is reached. And here's the equation. So I'm going to rewrite our equation out here. And I'm going to make a little bit of a table. So I make a table with I being initial. Some in the textbook, I think sometimes they write C for change, but this also means change. And then E stands for equilibrium. So I'm going to kind of annotate this with some blue so that we kind of know what some of these things mean. So this means initial, this means change, and this means equilibrium. Okay. So the stuff that I would write in red is what you would write on your quizzes or tests or whatever. And the stuff that I'm writing in blue is just kind of for our notes. So it says that initially, at the very beginning, the reaction contains 0.75 moles of carbon monoxide. So another thing, the only thing that goes in the ice table, only concentrations goes in here. So we're going to take our carbon monoxide it's 0.75 moles. I want to put it into a concentration. So I go 0.75 divided by 1. It's really nice that we're using a 1 liter container, so everything's just divided by 1. So 0.75 divided by 1 is just 0.75. So this starts with 0.75. 0. And that's moles over liters, or we can say molarity. And then we also have 0.275 moles of water. 0.275 moles over liters of water. Now this implies that it has not reached equilibrium, and that also implies that there is 0 CO2 in there and that there is 0 hydrogen gas in there. So we can put zeros in there. Now we don't know anything else yet, and it says after it has reached the equilibrium, analysis shows that 0.25 moles of CO2 are present. So I'm going to write 0.250 moles over liters, or molarity, is present. Okay. Now the big question is, like, how did this change? How did it go from 0 to 0.25? Well, this had to increase by 0.250. Okay. And that means since it is a 1-to-1 ratio, hydrogen had to increase by the same amount. So this also had to increase by 0.250 molarity. So this is going to be 0 plus this is 0.250 molarity. Since it's a 1-to-1 to 1-to-1 ratio, these things decrease by 0.25. And I subtract these things. This decreased by 0.25 as well. Okay, now that we have that, we can come up with our KEQ expression. So KEQ is going to be our concentration of CO2 times by our concentration of H2 divided by our concentration of CO and H2O. Now I input my values into my KEQ expression. The only thing that can go into KEQ is the equilibrium line. That's the only thing that goes in there. So I input my things in there. So KEQ equals 0.25 and H2 is also 0.25. CO, which is 0.5, and 0.025. So what I've done is, my first step is I made a table. I filled in the table and I watched my ratios. This was a really easy question because my ratios were just 1-to-1 to 1-to-1. And that's why it was like these values right here are all going to be the same. Now, I forgot to write a little negative right there, but if one side is increasing, then the other side has to be decreasing. So I then subtracted my changes. So 0 plus 0.25 is 0.25, and 0.275 minus 0.25 is 0.025. So I did all that stuff. And now I just have to calculate my unknowns. Okay? And so now I just have to put this into my calculator and write KEQ equals, and I have my calculator here, 0.25 times 0.25, or 0.25 squared, divided by 0.5 and divided by 0.025. And I get the value of 5. Okay? And technically I should be thinking about some of my sig figs that are associated with this stuff. And it should be 2 sig figs. Of that. And so my KEQ is 5.0. Okay? Okay. now we have another one right here, and it's a little bit more tricky, but we're going to go through this one. Anyways, so it says it gives us the KEQ this time of 3.5. It says that there's SO2, NO2, and it turns into SO3 and NO. So same thing as before. I'm going to make an ice table. So I write my equation, SO2, I write a little neater, and NO2 turns into SO3 and NO. Write my ice, like that, and now I'm going to input some of my values. So I read my equation, and it says I start with 4 moles of SO2 and 4 moles of NO2, and that's it. Okay. So, but most importantly, it's maybe not most importantly, but it's in a 5-liter container. So it would be wrong if I wrote 4 moles like this. That is not correct. It has to be only concentration is in there. So if I'm putting concentration there, I have to go 4 moles divided by 5 liters, or in other words, 0.8 molarity. This is also going to be 0.8 molarity. Okay, so now that I went 4 divided by 5, and I get my 0.8 molarity, and it doesn't say anything else. And it says it wasn't at equilibrium, and this implies that we started with these things, but we had none of these things. We can put zeros there. We didn't have any of that. And then it says what concentrations of all the species will exist at equilibrium. Now, what you have to kind of understand is that since you have no products, this has to increase this side. It cannot decrease. Like if this decreased by some number, it would go into negative concentrations, and that's not possible. So this side has to increase. If this product side is increasing, this side has to decrease. We don't know how much it's going to increase by or decrease by, but we do know that it's a 1-to-1 to 1-to-1 ratio. So in other words, we know that this is going to increase by the same amount, so X. And by the amount that this increases by, this is going to decrease by that amount as well, which is also going to be X. So we know that they're going to be the same values that are there. So we can just put that as X. So 0 plus X is just X. X. 0.8 minus X is 0.8 minus X. And now we input it into our KEQ expression. So our KEQ expression is our products, which is SO3 and NO, and SO2 and NO2. So input my values, KEQ equals SO3 and NO, which is X times X. Instead of writing X times X, I'm just going to shorten it up and write X squared. And then it's going to be over SO2, which is 0.8 minus X, and 0.8 minus X. And instead of writing 0.8 minus X times 0.8 minus X, I'm just going to write 0.8 minus X and then have that squared. And instead of writing my KEQ, we know what our KEQ is. It's going to be 3.5. So I'm going to write 3.5 in there. So now what I'm going to do is I'm going to solve for X. And so how I do that is my first thing I'm going to do is I'm going to take the square root of both sides. So I take the square root of 3.5, so root 3.5, and I get 1. Change my color back to red, 1.8708 equals, and the square root of X squared is just X, over, and the square root of 0.8 minus X is 0.8 minus X, like that. Okay. I'm going to multiply both sides by 0.8 minus X. So I go 0.8 times 1.87, and that's going to be 1.49. 1.49, and I have on my calculator 6, 6, 6, okay? And that's going to be minus, and then 1.8708 minus x is 1.8708x, that equals x. I'm going to add 1.8708 to both sides. Sorry, I'm going to add 1.8708x to both sides. So it's going to be 1.49666 equals 2, because there's like technically a 1 in front of that. So 2.8708x. And then I'm going to divide both sides by 2.8708. So divide by 2.8708. And I get 0.52. And we can just leave it at 2 sig figs, I guess. 0.52 is equal to x. Okay. So I did quite a bit of stuff there. Now let's go back to the question. It says, what is the concentration of all the species that will exist at equilibrium? So it wants to know what is the concentration of SO2, NO2, SO3, and NO at equilibrium there. So the easiest ones to do are SO3, which is going to be just what x is. So in other words, 0.52. molarity. And also NO, that one's pretty easy too, because it's just x. And we've solved that already. 0.52. Now the harder one, lightly harder, is going to be doing SO2. So we have to plug this 0.52. Let's do it in green here. I'm going to have to plug this 0.52 back into these values right here, into those little equations. And it's going to be 0.8 minus 0.52. And that is going to be, so I replaced that 0.52 in there. And then I can find out what NO2 is and SO2 is. So these are going to equal 0.28. Okay, and so that means that SO2 is 0.28. And NO2 is also 0.28. And so these are my answers. You don't have to do this part if you really don't want to. But if you're like ever unsure about this, and it doesn't work for all of the questions, but what you could do is you could plug these values. You could plug these values right here back into your KEQ expression, and it should equal 3.5. So if I go SO3 and NO, so in other words 0.52 squared, and then I divide it by 0.28 squared, it comes out for me, like there's a little bit of rounding errors and stuff like this, but it comes out to me of like 3.45, right? So really, really darn close, and it is probably because I like rounded and stopped some of those numbers right there. But since it comes out to 3.45, which is really darn close to 3.5, I'm pretty confident that all these values are correct. Okay, so it's a little thing that you can do, just like double check to see, am I right? Okay, anyways, if you have any questions, please come and find me.